Hello, I'm Sue Nelson and welcome to the Planet Earth podcast. Lady Gaga says she was born this way, and apparently, when it comes to personalities, so are sticklebacks.
The order which we catch the fish correlates with their boldness score in the tank. So if they're caught first, they're extremely bold in the tank, and if they're caught last, they don't go anywhere in the tank, they're extremely shy.
And trust me, that's not the only piece of information about shoaling fish that will blow your minds. And you can hear more a little later on in the podcast. This time, we're in Cambridgeshire at the British Antarctic Survey. Well, just outside the building to be precise, with the roar of the M11 in the background, because the cause of our first item can be seen in daylight up in the sky. The sun, that star at the centre of our solar system, 93 million miles away, is in a constant state of activity. It spews out a stream of charged particles in the form of solar wind, produces solar flares and explosive coronal mass ejections. This space weather affects our planet, and so it's important to be able to predict space weather accurately. And this is where the British Antarctic Survey comes in, as it produces Spacecast, an international collaboration that helps protect satellites by forecasting particle radiation from the sun. Well, Spacecast project coordinator Professor Richard Horne joins me now. Richard, we can just about see the sun through the leaves and the tree above us here. What's actually going on right now?
The sun goes through an 11-year period of activity, which we measure by the sunspot cycle, and that's a good measure of activity on the sun, but it also has an important impact here on the Earth. It takes approximately 2 to 3 days for material flowing off of the sun to reach the Earth, and when it does, it actually interacts with the Earth's magnetic field, disrupts the whole Earth's magnetic field, and then that can actually have bad consequences for satellites, for power grids, for prospecting for oil and gas, for a whole range of different businesses here on Earth.
I think people are probably quite familiar with some of the extreme effects of space weather. About 9 years ago, there was a big effect in Sweden with power going down. In 1989, there was a famous one in Quebec, in Canada, where a whole city practically lost power. But they're two events in about sort of 25 years. How much damage is being done by space weather on sort of, a shorter time scale?
Space weather is not just restricted to those sort of large events. We do have much smaller events which occur, and they may occur maybe in periods of high sunspot activity, one a week, one a month, something like that. Generally, they tend to be minor, sort of things that happen on satellites. They may have sort of memory upsets, or they may have some glitches in their operations, which usually they can deal with. For the power grids, they may have additional loads on the grid itself, which they've got to generate more electricity to try and overcome and try and combat. What's really important at the moment, and as we move into the next few years, is that we're a period of solar maximum where the activity is much, much higher, and the number of events like this is actually going to increase. And there is also a likelihood, a really important danger, that we may have an extreme space weather event, which may have really quite important consequences. Back in 1859, we had the largest magnetic storm on record. That was known as the Carrington event. What would happen if that occurred tomorrow? We know that we've had power blackouts in the past in Quebec. Could we have a power blackout in the UK, and how long would it last? It's a very difficult thing to assess, and we don't have very much data. We rely on satellites these days more than ever before. There's about 1,000 satellites up on orbit right now, about 400 or so in geostationary orbit. We rely on it for all kinds of things, for Earth observation, remote sensing, for weather forecasting, TV, banking, for internet access, for navigation signals, for positioning, all kinds of ways which couldn't have been foreseen even 10 years ago in many cases, and that is going to develop. Our reliance on satellites is going to increase into the future.
Well, let's go, much as I'm loath to say it, out of the sunshine and go inside the building then to actually see this Spacecast in action and meet a couple of your colleagues who are also working on it.
That sounds good.
Right, we're inside your office, Richard, and we're joined by Dr. Sarah Glowett and Nigel Meredith. And this is it. This is Spacecast. It's basically lots of graphs on a computer.
That's right. We're making a forecast right now. We're taking information from various satellites and from ground-based stations. We're putting that into a computer model, and we're forecasting up to 3 hours ahead what the radiation levels are in space for satellite operators.
Nigel, you're involved in some of the input that actually goes into making a forecast. What sort of things does this computer simulation need from you?
That's right. I'm producing models of the waves in space, which have an influence on the radiation belt environment. I've put together a database of waves from 5 different satellites, incorporating data from approximately 16 years' worth of observations, to produce a global model of the waves in space.
When you say waves, which waves in particular do you mean? Microwaves, radio waves?
These are low-frequency waves at the lower end of the radio spectrum, with frequencies typically between about 20 hertz and 20 kilohertz, so they're in the audio frequency range.
Oh, audio. So does that mean we can hear them?
It means we can play them back and listen to them as if they were the natural waves as they actually occur. And I believe we have an example on the computer that we can listen to now.
Sounds like it's on a bit of a loop there. Not quite what I expected. It's a little bit Doctor Who, not helped by the fact that you've got some quite groovy graphics to accompany it.
Well, that wave that you just heard there was Whistler mode chorus, which is a particularly important wave which can accelerate particles in the radiation belts up to very high energies. And that's one of the emissions that we observe.
So they're sort of, in a way, there's like particles are surfing on these waves. The faster the waves, then the quicker they get here.
That's right. The particles themselves can actually surf on the waves and gain energy, gradually in small increments, but by surfing on many waves over time, they can build up their energies to very high energies, up to the so-called MEV energies, which are representative of the killer electrons, and they can be accelerated to these kind of energies on the timescale of typically 1 or 2 days.
Now, Sarah, you're putting then this information into the simulation. How difficult is it to make a simulation of space weather forecasting? Because there must be quite a few variables, because they're not just these waves that Nigel's talked about, but there are other aspects of space weather as well that you need.
Yes, I mean, we certainly need, for instance, the activity of the sun, the levels of geomagnetic activity going on out in space. They all go into the model. There are various other waves that interact in different ways and drive the particles closer to the Earth, generally, that sort of thing. They're all different aspects that go into the model.
And how accurate is it? How do you test its accuracy?
OK, we developed the model by running it as a simulation, not as a forecast. So there are periods of time for which we have satellite data that we can actually try and recreate using the model. So that gives us some idea of how well we're doing. There's also limited satellite data available most of the time that, again, we can run the model and check against it. And if you look on the Spacecast pages, you'll actually see data from the GOES satellite and a model prediction of that data. So you can actually tell for yourself how well we're doing. And you'll see there are times at which we do well and there are times at which we don't do so well.
And what are the timescales involved here? What's the timescale between effectively the sun belching and us feeling its breath?
That can vary. The fastest material can flow off of the sun and reach the Earth. It's something like 17 hours. That's a very fast coronal mass ejection. But typically, usually, it's around about 2 days, 2 to 3 days, something like that. And then once that hits the Earth's magnetic field and disrupts the Earth's magnetic field, that's when all these waves come into play, accelerating the charged particles. And that's a process that occurs inside the Earth's magnetic field. And that then may take typically a day, maybe 2 days, something like that.
Sarah, how far ahead can you make these forecasts?
Well, we're currently forecasting up to 3 hours ahead. We're limited in how far ahead we can forecast by the data we receive from satellites.
You do tend to associate British Antarctic Survey with penguins and ice sheets, don't you? But you're a physicist, aren't you, Nigel?
Yeah. One reason why the British Antarctic Survey is involved in space weather is because both the Antarctic and the Arctic are basically our windows in space. When you have activity occurring in the Earth's radiation belts, you can get signatures on the ground, such as enhanced auroral activity, and these are only typically observed at higher latitudes, such as in the Arctic and in the Antarctic, where we can observe the optical signatures and also the sounds, if you like, of the magnetosphere with VLF receivers.
Richard, you're a co-investigator on a NASA mission that launched only a few weeks ago to study the sun's influence on the Earth. How will this mission complement what we already know?
The Radiation Belt Storm Probes is a very important mission. It's going to measure very low-frequency radio waves, very different types of them, and that's going to help us improve the forecasting system. We're going to access that data, process it, and then include that into our models and help verify our models and actually improve our forecasting capability. It's going into a region where we don't really have very much data, so that's very important for us. And here at the British Antarctic Survey, we have a co-investigator status on the mission. I think we're the only UK group to have that, and that's very important for us. And it's a very important international collaboration.
Right, well, before we actually take a look at what the Spacecast forecast tells us today, Richard Horne, Nigel Meredith and Sarah Glowett, thanks very much for now. We'll be back at the end of the podcast, though, to watch a space weather forecast in action. This is the Planet Earth podcast, and pictures of our guests and the Spacecast forecast at the British Antarctic Survey can be seen on our Facebook page or via our Twitter feed. Whether you belong to a book club or have walked with hundreds of other people to a football match or even the recent Olympics, you will have been part of a group dynamic. Studying group behaviour has a number of important applications, so Richard Hollingham joined behavioural ecologist Dr. Andrew King at the Royal Veterinary College in Hertfordshire. They met inside one of the rooms that's part of the Structure and Motion Laboratory, and it was filled with tanks of stickleback fish. Why? Well, it's to find out how personality and making decisions as a group, such as in shoals, can tell us more about people than you ever thought possible.
We've got two populations here of about 50 or 60 fish in each case, and the lower tank that we're looking at have just been involved in some behavioural tests, and these are actually individually marked with little elastomer tags, which is just a little plastic tag which we just inject under the skin so we know which fish is which.
And what sort of experiments are you conducting here?
Okay, so what we do is we take individual fish and we put them in this arena which we have to our left here, and this arena has individual tanks with lanes in it in which we can test how bold each fish is. So the tank has a very scary shallow end and a very kind of friendly deeper end, and what the fish tend to do is stay in the safe end, and if the number of occasions and how long they spend at the scary end gives us an indication of how bold those fish are. And so what we then do is we get an order of how bold fish are from 1 to 100, for example.
So these fish, although they look, if you look inside the tank, and each one is about 3 or 4 centimetres long, lovely glinting shiny colour, they have different personalities.
Yeah, so what we find is that when we put them in these lanes in which we're looking at how much exploration they do, that they do vary considerably according to the identity of the fish. And the important thing is that this variability is consistent within an individual. So fish A will be bold on day 1, and if we retest him 1 week later, he'll also be bold on day 7. And the great thing is that we found is that when we collect the fish from the tank, so I'm just with the net picking the fish up to take part in this test, the order which we catch the fish correlates with their boldness score in the tank. So if they're caught first, they're extremely bold in the tank, and if they're caught last, they don't go anywhere in the tank, they're extremely shy. So it's a really nice indication that what we're measuring is something real.
And you've then categorised them. So you've got these categories of, what do you call them, quite scared, quite bold?
Yeah, it's called a bold-shy continuum, so it varies according to the fish. Once we have that, then we put them in these tanks which we have to our right-hand side.
So these are much smaller individual tanks, all numbered in a rack of shelves, all the way up the wall from what you've got. How many tanks have you got?
60 here.
60 tanks.
Yep. So we have 60 tanks in front of us, and each tank is in the same water system, the same filtration, all of the nasties are all filtered out of this. And each fish stays in here during the behavioural tests, and we feed each fish so we know every fish gets the same amount of food, and we control their social environment so they can see each other in these tanks. So they're very social animals, so we don't want to deprive them of that. So they can see one another, and we rotate them so they don't get used to being next to certain neighbours. And what this means then is that we have individual fish that we know how bold they are, we know how much food they've been getting, we know they haven't been interacting with any males or females recently, and we combine these fish into different categories of bold or shy individuals, and we make up shoals composed of mostly shy, mostly bold, a mix of the above. And what the idea is to try and test what combination of these different personality types creates a winning team, if you like. What combination of these personalities creates the best shoal?
So a shoal might consist of all bold or all a little scared, or a mix of the two.
Yes, exactly. And in the wild, what we find, if you try and catch a population, it's hard to catch a whole population, but if you catch a sample, then what you tend to find is that you get lots of shy individuals and relatively few bold individuals. So what we try and do is try and work out why on earth that combination would be a crucial or optimal combination of fish to have. So we make these different shoals, and we give them tests like try and find food in this new novel environment, or try and avoid this predator, and then we see which of these different shoals performs best.
Now, is this really to just understand shoaling, understand the process by which fish move as a mass?
Yeah, exactly. So that's the one aim, is to understand exactly how those individuals shoal, what rules they're using, how they follow fish. Are they following all of their neighbours, 1, 2, 4, 5 neighbours? And that relates to a lot of work in kind of flocking animals and shoaling fish and flocking birds. But the other thing that we want to try and work out is, if animals have this personality, why on earth is it adaptive? Why should you vary? And so this is trying to get to the grips of, it might be beneficial when you combine all these individuals do better by pairing up with those which are different from them.
So you need a population with a mix rather than all bold or all of a certain personality type.
Exactly, that's the idea we're testing and finding some evidence for at the moment.
Why do this? I mean, it's interesting, but what's the point of it?
From a pure behavioural ecology perspective, we touched on that just now, is that we want to understand the evolution of these personality differences. But from a broader perspective, I also do work with human groups and different ungulates and primates as well, and to try and work out what combination of personality types and characteristics make a winning team is of interest for economists, basically anyone who's interested in information sharing in group kind of societies. Maybe it's a little bit of a jump, but it works surprisingly well across these different species.
So you're saying the same rules that apply to a shoal of sticklebacks could apply to a team?
Yes, so colleagues in Princeton University, a colleague of mine called Ian Cousin has recently done work with fish very similar to this, and has shown that they use quorum rules, and basically that a certain number of fish have to agree on choice A or B before the whole shoal makes that decision. So it's majority decision making, just like we would call a democratic process. But there are other scenarios which we're testing in the laboratory here where you very definitely see that they're following a specific individual that maybe have pertinent information or a particular characteristic that makes them a leader. So we can almost manipulate the environment to generate different decision-making mechanisms, which we see in our own species.
That's incredible that there are basic rules, or this suggests there are basic rules underlying the way fish or higher animals or us interact.
Definitely, and one of the things that keeps emerging from my research is leadership and followership. There's two social roles that these individuals adopt, and there are surprisingly common principles across many different species, from fish to birds to humans to ants.
Are these rules, if you like, pre-programmed into the fish? Is a bold fish always a bold fish, or can it change?
Now, that is a great question, and that will be the next grant proposal. So what we're finding is there's consistent differences across individuals, and that they adopt different social roles, but we don't know to what degree that is fixed. So the way we'll do that is to have individuals from hatching in different conditions and track their personality through time, and basically to see if individuals are born this way or are made this way. So a leader's born or are they made is kind of the next thing that we're looking at.
Andrew King from the Royal Veterinary College on the fascinating applications of studying bold and shy fish, not least the additional bonus of enabling people to improve the management of wild populations of animals. Well, I promised you a space weather forecast, and even though by the time this podcast goes out, it's probably out of date, we're going to do one anyway with Richard Horn, Nigel Meredith and Sarah Glowett. OK, who's going to take me through what I'm seeing on a screen here? Some nice multicoloured graphs, green, blue, sort of a hippie LSD style colours there. Tell me then, what is this forecasting?
We like to make our forecasts interesting, lots and lots of different colours. So at the top panel, what we're actually showing is the energetic electron flux, the number of particles that are trapped in the Earth's radiation belts. And that is actually just increasing over the last few hours. And what we're showing is that geostationary orbit, the risk of a satellite going wrong is actually quite low at the moment, but the risk of a satellite near medium Earth orbit, which is where the navigation satellites fly, is looking a lot higher. We've just come out of a magnetic storm from a few days ago, and the activity is sort of ramping down a little bit. The solar wind speed, we have a measurements of the solar wind from the ACE spacecraft. That's around about 500 kilometers per second, which is a little bit high. And we have measurements of the interplanetary magnetic field, the direction of the magnetic field in space. That's a key parameter to work out whether we're going to have a high risk forecast or whether we're going to have a low risk. Usually when that polarity of the magnetic field goes southward, then we tend to have a much more active conditions, much higher radiation belts.
I've had Richard's verdict. Do you too, Sarah? Nigel, do you agree with him?
Yes, pretty much.
Good, I'm pleased to hear it. Richard, Sarah and Nigel, thank you all very much indeed. And that's the Planet Earth podcast for the Natural Environment Research Council. Don't forget to check out our Facebook page and our Twitter feed. I'm Sue Nelson from the British Antarctic Survey in Cambridgeshire. Thanks for listening.